In this video, we use factorial, double factorial, and gamma as expansion coefficients of the Taylor-Maclaurin series sum for R cosine. So we begin with the R cosine dataset. And here's the R cosine dataset. And we insert chart. And we use scatter chart. This row 1 as header, series, show the trend line, polynomial to the 8th degree. And the label, use the equation. For the legend, position at the bottom or maybe on the left. And the horizontal axis, the number format, none. For the vertical axis, show the axis line. That's the axis line. And the number format, we'll change this number format to none. None. That's the number format, none. And here's the trend line. And polynomial to the 8th degree. And next we will calculate the expansion, the Taylor-Maclaurin series sum expansion of this. So which is the summation of is 0.5 minus the summation of a times x to the power 2n minus 2n plus 1, where a, the coefficient, can be factorial, double factorial, or gamma, and the value n, 0 to infinity. In this case, 16 is good enough for approximation. So we continue with the gamma coefficient. So array formula, gamma of n plus 0.5. All over. The denominator has 3 parts. The first part is 2n plus 1. So 2 times n plus 1. That's the first part. And because there are 3 parts, so we add another parenthesis here. So the second part will be factorial of n. Factorial of n. That's the second part. And find the third part. Square root of pi. And enter. So here's the trend line. The expansion coefficient of the gamma function. We continue with the double factorial. R formula. That's factorial double. So that's double. Double factorial 2n minus 1. So 2 times n minus 1. That's the numerator. Now the denominator. The denominator has 2 parts. Double factorial n and the quantity 2n plus 1. So double factorial n. That's 2n. So double factorial 2 times n. 2 times n. So double factorial 2n. That's the first part. And the second part. The quantity 2n. 2 times n plus 1. And enter. You will notice these are exactly the same except for the first item. We'll correct that. So if n equals 0, it should be 1. Just like the other. So it should be 1. So we'll correct this. So if n equals 0, then 1. Otherwise, calculate. So here you have the expansion coefficient in gamma and double factorial. We continue with the factorial form. Array formula. The numerator is factorial 2n. So factorial 2 times n. That's the numerator. Now the denominator. There are three parts. So the first part is the quantity 2n plus 1. 2 times n plus 1. That's the first part. Now the second part. The second part is the quantity squared. So that's a quantity 2 to the power n times, within that quantity there's factorial n. Factorial n. And all raised to the power 2. That's squared. So enter. Now all these are exactly the same. You can use any one of them as expansion coefficient. Now we continue with the expansion, which is array formula. We begin with the first part because there's 0.5 pi times the summation. So SERIESSUM of the x values raised to the power 2n plus 1. That's x to the power 2n plus 1, where 2n plus 1 starts from 0, or times starts from 1. And followed by 2 times 1 plus 1, 3. So 1, 3, 5, 7, 9. So the increment is 2. And the coefficient. You can choose any one of the three. So start with the factorial. And we'll show the polynomial. Edit chart. Trend line. Polynomial to the 8th degree. The label, use the equation. Now we got the equation. So, and next we will calculate this polynomial regression coefficient using LINEST. To do that, we complete the LINEST matrix. So this will be transpose 0 to 8. Then enter. Transpose 0 to 8. I think that should be okay. Enter. Now we go to the elements. Array formula of the x values raised to the power 0 to 8. Then enter. Now we can use LINEST to calculate the polynomial regression coefficient. LINEST starting with the function itself, r cosine. That will be our data y. And data x. And the expansion, LINEST, data y, and data x. Then enter. Right now we have different coefficients, but we can modify that later. So what's next is we factor in 0.5 pi, and it is 0.5 pi minus the summation. So enter the negative sign for this. And finally, add in 0.5 pi. So 0.5 times pi. And enter. Now they're all in the same trend line, and their polynomial regressions are the same. We'll check coefficient of x to the 0, 1.57. Coefficient of x, -1. Coefficient of x squared, 0. This is 0. 4.44 times 10 to the minus 15 minus 17. X cubed, that's 0.172. Negative 0.172. Negative 0.172. X to the fourth, 0. Because this is 4.4 times 10 to the minus 14. That's already 0. 1.16 times 10 to the minus 15. That's already 0. And x to the fifth. X to the fifth, 0.0361, 0.0361. That's negative 0.0361. X to the sixth, this is 0. 1.4 times 10 to the minus 13. And that is 10 to the minus 15. That is already 0. X to the seventh, 0.132. That's negative 0.132. Negative 0.132. X to the eighth. That's 1.27 times 10 to the minus 13 times 10 to the minus 15. Those is 0. So suppose I change this to the double factorial. We'll change this to the double factorial. We use the double factorial as coefficients. We still get the same polynomial. Regression coefficients, our polynomials still the same, and our data sets are still the same. Suppose I use the gamma. I'll use the gamma. This is the gamma. Then enter. Again, the data sets remain the same. The lines are still the same. Polynomials are still the same. And the regression coefficients, they're still the same. This completes the use of factorial, double factorial, and gamma as expansion coefficients of the Taylor-Maclaurin series sum expansion of arc cosine x.